Hi, I did an unboxing of this UTG4082A in my last video, and today we're going to dive a little bit deeper and comb through some of its features. For those who haven't watched my previous video, the instrument here is a dual-channel 80 MHz arbitrary waveform generator from UNI-T. I will leave a link to the product on UNI-T's website in the video description below for you to learn more at your own leisure. Very briefly, here are some of the highlights from the specs. The UTG4082A has a 16-bit output DAC with an output frequency of up to 80 MHz. In the UTG4080A series lineup, this one has the lowest spec. The top-of-line model is the 4202A, which has a maximum output frequency up to 200 MHz. All models in this 4000A series have two output channels, a sampling rate of 500 megasamples per second, and they all have a waveform memory depth of 32 megpoints. I think what I'm going to do in this video is breezing through some of the basic functionalities and concentrate on some of the unique features this instrument offers, as its basic operation is very similar to the other UNI-T arbitrary waveform generators I had reviewed on this channel in detail. And you can check out my UTG9062E and UTG1042X review videos if you want to learn some of the basics. Also, I will be using my HP8566B spectral analyzer in this video to show you the spectrum of the output from the 4082A. And since the spectral analyzer is quite noisy, I'm going to save the tests that require the spectral analyzer towards the second half of the video, so some contents will be a little bit out of order. Now, of course, the lab is already noisy enough. You hear the AC running in the background and some of the instruments' fans are on. But I wanted to, at least for the first half, to concentrate on some of the other functionalities. Originally, I was planning on using the UNI-T UPO1204 oscilloscope in this review to test the output from the UTG4082A. But the oscilloscope is a little bit too wide for me to capture both the screens of the arbitrary waveform generator and the oscilloscope. So I swapped in my Mixig STO1004, which also has a larger screen, so you should be able to see the waveforms without me having to constantly zooming in and out. And by the way, the STO1004 is an excellent oscilloscope from Mixig. You can check out my review video of the STO1004 if you are interested. Anyway, let's get down to business. Right now we're outputting a 1 MHz sinusoidal from the signal generator, and you can see that waveform captured on the Mixig. Of course, the operation, as I mentioned, is very easy. All you do is come into your waveform and you can change using the knob here to change different aspects of the parameters. Let's just say we want to change the frequency here. Then you enter and you can use the knob to change the frequency. You can see that it is reflected on the oscilloscope, or you can use a keypad here. So let's say we want 5 MHz. You can do 5 MHz and then voila, we can see the updated waveform on the oscilloscope. And while you probably can't see it, we do have the measured amplitude of roughly 1 volt, which is exactly what we're outputting here, 1 volt peak to peak. Of course, this is a 80 MHz arbitrary waveform generator, so we are expecting we would be able to output 80 MHz sinusoidal. So let's actually do that, just for a quick verification here. So let's do 80 MHz. And you can see we are able to output 80 MHz. Of course, right now the amplitude dropped to 780 millivolts. Now that could be a couple of factors. It could be the output attenuation and also the cable and also your oscilloscope. But nevertheless, that is definitely within the 3 dB bandwidth. Now let's take a look at the square wave. You can see that we have this section of the buttons here. Those are for you to switch between the different waveforms, which is very conveniently laid out. So let's press square. And of course, right now, the square wave maximum frequency, you can see we dropped to 30 MHz. That's also according to the specification. Anyway, let's reduce the square wave frequency a little bit, as because of the square wave's rise time is not as fast, you do see this distortion here. So let's actually reduce the frequency to, say, 1 kilohertz. Let's do that. So the frequency, let's do 1 kilohertz, and let's acquire the signal. And bingo, you can see we have this square wave nicely displayed. And for the square wave, the rise time is fixed. So let's take a look at the rise time here. So let's expand it. You can see, not sure if you can read this, but it's at roughly 7 nanoseconds, which is definitely what is specified. Now, this one is independent of the frequency. You can see here we can change the frequency to, say, 10 kilohertz. Let's do, by the way, you can use left-right arrow to select each individual digit and adjust that way. So let's do, for example, 100 kilohertz. You can see that we're not affecting the rise time at all. So anyway, so let's get back to 1 kilohertz. And you can see that the rise time is at 7 nanoseconds, not impacted by the frequency of the waveform here, which is similar to the 962E and 1042X we had reviewed before. Of course, you can also adjust the duty cycle as well. And as I mentioned, in the square wave mode, the rise time is fixed, but you can change the rise time if you change to pulse mode. So let me demonstrate that. So for example, right now we're in pulse mode. Everything is exactly the same. As you can see, this is still a square wave because right now we're at duty cycle of 50%. Now the additional feature here is that you can change the rise time here. So for example, by default, we're again at 7 nanoseconds, and that is actually the fastest you can go. So for example, right now I can change it. I can't change it down anymore, but I can change it up. So you can see we can do all the way up to, let's see how far we can go. I think we can go quite a bit. Yeah, you can go definitely quite a bit. So anyway, so that's how the rise time is controlled here. Let's change it back to 7 nanoseconds. And you can see here, then we can change the duty cycle here. So let's do a 10%, and let's reacquire the signal here. And that's our pulse signal. And of course, we have the ramp signal you can see, and you can adjust the symmetry here. Let's do that, which is very nice. And of course, we have some built-in arbitrary waveforms. So the built-in arbitrary waveforms, you can see we have a lot of them. And here is a list of built-in ones. You probably can't read the labels, but we do have a lot. So for example, the pulse, and let's select another one, stare up, stare down. Yeah, you can see we have a lot of these. And you can adjust the frequency, amplitude, offset individually. And of course, we have some other arbitrary waveforms stored as well. And of course, you have other functions like math. Let's do another one. Now you get an idea. The arbitrary waveform generation is quite rich. We have a lot of arbitrary waveforms built in already. So let's take a look at a few. Let's do a bio. This one, what is that? It's a pulse. And for each of the arbitrary waveforms, of course, you can control the frequency, offset, and the amplitude. And of course, you can also do modulation on top of the signals. We'll demonstrate a few. So let's go back to sinusoidal here. This is a 1 kilohertz. Let's do the carrier frequency of 1 megahertz. So that would be easier here. And let's do modulation. That's external. Let's first change it to internal. We'll take a look at external a little bit later. So right now we're modulating a 1 kilohertz signal on top of the carrier. Let's change the trigger here. That's our modulated signal. And of course, the modulation depth is 100%. We can change that. We can change any of these, for instance. So let's change the frequency. You can see that we can change the modulation frequency. We can also change the modulation depth. So let's reduce the depth. You can see those are reflected instantaneously on the oscilloscope. There are a lot of built-in modulation types that are supported. You can see right now we're doing amplitude modulation, but if you come here, you can see we can do frequency modulation. Let's actually take a quick look here. So this is obviously a frequency modulated signal. Let's auto-acquire that. And you can see the modulation here. Well, obviously the frequency deviation right now is too high. So let's come down here, change it to, let's see, 100 kilohertz. That should be plenty. And you can see this is our frequency modulated signal. And let's try out a few others. So here, let's see, we have the phase modulation, and you will see very similar waveforms compared to the frequency modulation. Let's go down and change the frequency to 100. You can see that we can already see the phase shifts from the display here. And obviously the phase and the frequency are related. In this case, the resulted waveforms look fairly similar, but the mechanisms are slightly different. And you can see here, let's drop down. By the way, not sure if you can read or not. Let's actually zoom in a little bit. So you can see we have AM, FM, PM, ASK, FSK, PSK, BPSK, QPSK, OSK, QAM, and PWM. So we have quite a few of these different modulation types. So let's just look at a few more. Let's look at ASK, which is amplitude shift keying. And here is our ASK signal. Let's change to another one. Let's see if we can see frequency shift keying. And here is the capture waveform of frequency shift keying. You can see we have two frequencies modulated on top of the carrier frequency here. Essentially, this modulation works by shifting between the two frequencies at the specified rate. Here is 59 kilohertz. Now, of course, we have a lot of other options we can test. The phase shift keying, that's probably very similar. Let's do the BPSK. Now let's briefly take a look at the binary phase shift keying here, and that essentially is using two different phase signal to modulate the carrier frequency. So you can see here, right now we're changing the phase to be 180 degrees, so these two signals essentially have the opposite phase. Let's briefly pause the capture here. You can see, let's see here, sometimes it's a little bit difficult to capture the signal here, but once in a while you do capture a signal, you can see we do have this abrupt phase shift here. Obviously, I won't be able to show you all the modulation types in detail in this video, but I will save a few more till a little bit later. Because the UTG4082A supports external modulation, I can actually use it to demonstrate how an AM radio transmitter works. So here I have a simple microphone amplifier circuit board, and the output is connected to a BNC, so I can plug it into the external modulation input. And of course, it's powered by a 9-volt, so there's nothing fancy. So let me actually hook it up, and we'll take a look. All right, I have plugged it in. The BNC cable is a little bit short, but nevertheless, I plugged it into the external modulation input and also powered on the circuit board with a 9-volt battery here. And here I have an old radio with tuning knobs. These are analog controls. It took me a while to find this one. As you can see, it is quite dirty, quite beat up. That's because it hasn't been used for more than 20 years. These simple radios are hard to come by these days. I have quite a few digital ones lying around, but this is the only one I can find still with this old-fashioned manual tuning knobs. Anyway, let me turn it on. And of course, right now it's garbage. So let's actually lower the volume a little bit. And right now, let's see, change the frequency here. So let's go back to sinusoidal. And we want to do the frequency within the AM band. So let's do, I don't know, let's do 1.5 megahertz, I guess. That should be fine. 1.5 megahertz. And let's do the amplitude, we'll leave alone. Let's do the modulation here. So modulation, obviously we want to do AM. And that should be fine. The modulation source right now is internal. Let's do external. Actually, let's do internal first, because right now we're modulating with a 500 hertz signal, so we should be able to capture that on the radio here. And of course, for us to be able to receive through the radio, we have to add an antenna. So let me disconnect the BNC cable, and let me add in a whip antenna here, so we can try to see if we can capture that signal. I had to change the frequency down a little bit because you can see here, now I changed it to 800 kilohertz because 1.5 megahertz, that band has a lot of noise. I don't know why. I'm in the basement, there's a lot of equipment going on. Anyway, so right now we're changing back to 800 kilohertz. So let's go back to the modulation. You can see we're having a 500 kilohertz signal right now modulated on top. So we should be able to find it. Let's see. And you can hear that is essentially our internal modulation. Right now it's emitted from channel 1. And if you don't believe it, let's turn it off. And you can see that's indeed our modulation here. So anyway, we have that set up. Now let me enable the external modulation here. So the modulation, let's do external. So I should be able to talk to the microphone here. So let's see here. Let's turn on the volume here. Hello, And you can hear this is actually from the AM broadcasting. So that is, whoops, let's put it back here. So that is very, very cool. And that's just a quick demonstration of the external modulation capability. You can use the external source for other modulation types as well. Unfortunately, the maximum output frequency of the 4082A is just below the spectrum for FM broadcasting. Otherwise, I would have been able to demonstrate the FM broadcasting using similar method as well. Anyway, you've got the idea. So let me change it back to internal before I forget. And let's take a look at some other modulation types. Now, one of the very powerful feature of this arbitrary waveform generator is it supports some modulation. You can see here, that's the modulation type. And some modulation is very powerful because you can modulate an arbitrary waveform with another arbitrary waveform. Although a more typical use of a sum modulation is to modulate a percentage of a Gaussian noise onto the carrier waveform. Anyway, let me do a quick demonstration here. Let me put the BNC cable back in, and that's our AM modulation. So let's change it to sum. And right now, the waveform is sinusoidal, so let's change it to, let's do this, change it to noise. And let's do depth of, let's say 10%. And let's acquire the signal. And you can see the capture signal, we have quite a bit of noise on top. That's because we're modulating noise on top of the sinusoidal here. And if I decrease the noise, you can see that the waveform gets cleaner. And if I increase the noise level, you can see that it gets a lot noisier. So that's just a quick demonstration of the sum modulation. Another modulation type the UTG4080A series support is quadrature amplitude modulation. This modulation is commonly used in wireless communications. It essentially uses two orthogonal carrier signals, both the in-phase and quadrature components. Sometimes quadrature amplitude modulation is also referred to as IQ modulation. Anyway, let's take a quick look. And I'm going to zoom in a little bit so you can actually see, because this is a modulation type a lot of people haven't seen before. So let's come to the modulation type. And you can see we have this QAM, and that's quadrature amplitude modulation. And we come here, and you can see there are already a few parameters you can select, one of which is the constellations. So right now we have 16 QAM. Essentially, we're sending 16 symbols. You can see here, those are illustrated by these dots. Now, of course, we can change it to 4, we can change it to 8, and you get an idea. The maximum this one supports actually is quite high. Well, let's actually show you what the 1280 looks like, and of course, the highest one is 2560. So let's go back to 16, as this one is probably easier for us to illustrate. A commonly used technique for observing this type of signals is to use eye diagram. Now, we should be able to produce an eye diagram. The majority of low-end scopes typically have issues producing eye diagram because most lack the clock recovery capability. But here we have these repetitive signals, so we should be able to get something on the mixsig. Now, to produce an eye diagram, you will need to trigger on the frame instead of the rising edge of the actual signal. This is where the external trigger comes in. So we will have to use a sync signal putting into channel 2. Let me set that up. Alright, so now I have put the sync output connected to channel 2. So let's actually change the trigger source to see if I can figure out this. Trigger. Let's do source channel 2. And we're triggering here. So let me adjust the oscilloscope a little bit, and hopefully we can get a stable eye diagram here. I have to change a few parameters to get this stable output. You can see that this is actually a pretty nice eye diagram. You can see what we did here is we essentially set the persistence to 5 seconds, and we also changed the trigger to key off channel 2, which is the sync input. So that's the eye diagram. And of course, we have also changed the signal generated output. And you can see right now we're outputting a 1 MHz carrier frequency, and the modulation is 16 QAM at 1 kHz. So that's the eye diagram you are looking at. As mentioned earlier, not all entry-level scopes can display this eye diagram as clean as what we can see on the MIXIC. And on higher-end scopes, obviously you will have dedicated function for eye diagram display, but for entry-level scopes, this is as good as it gets. The UTG4082A also supports DC output. This is a common feature on a lot of the arbitrary waveform generators, and you can use that to essentially output a DC using that as a voltage source. Of course, because we have 16-bit output, so I would expect the output to be a little bit more accurate compared to the other 12-bit output ones. So right now you can see here, let me just zoom in a little bit. We have selected the output to be DC here, and right now we're outputting 0 volts. Let's increase the offset here. Let's do 1 millivolt here, and you can see we're exactly 1 millivolt. 2, so that is definitely very accurate here. 4, 5, yep. So let's do just 1 volt at a time. Of course, you can go both positive and negative. So let's do 1 volt. Let's do, 1. Let's try again, volt. So you can see we're essentially showing 1 volt, pretty much spot on. And let's do 2, 3, 4, 5, no problem. I think it goes all the way up to 10 volts. Yep. So you can see that's the plus 10 volts, and of course we can also go negative. No problem. And definitely you can use this as a voltage source in a pinch. And of course, the 4082A is a dual channel one, so we should be able to use both channels. And one useful application is that if you want to generate 2 signals of known phase difference. So let's take a look at that demonstration here. Right now, I'm outputting 2 1 kHz sinusoidals. Both are in phase currently, and we can adjust the phase of one of the signals. Let's do that. Let's do phase 2, for example. We can change it 1 degree at a time. And you can see that the phase relationship between the 2 signals are reflected on the display here. So let's do 90 degrees, and you get the idea. And of course, if we change the display to XY mode, we would be able to see the Lissajous figure displayed here. So let's do that. So let's change to XY. And you can see right now we're showing as a circle because these 2 signals are 90 degrees apart. So of course we can adjust the phase differences. You can see that we're essentially changing to now a straight line because now these 2 are opposite phase. But of course if we change to 0, let's do phase 0, and now they're in phase again. There's just so much I can talk about of this 4082A, and there's a lot we haven't really touched upon. One thing you can see here is right now channel 2 is doing the sweep. We are sweeping linearly between 100 Hz and 5 kHz within a time frame of 10 seconds. You can see that's a generated Lissajous figure on the scope. Alright. For the remaining demonstration and experiments, I will need to turn on my HP8566B spectral analyzer, and it will be a little bit noisy. The first test I'd like to do is to check the output spectral purity of the sinusoidal output. So for that, I have hooked up the spectral analyzer with this DC block, as you can see here. Let's actually start with 10 MHz here. So let's do the frequency as 10 MHz. Let's do that. And the output should be just fine. Let's take a look at the spectral analyzer here. And you can see the output spectrum is very, very clean. We're looking at a span of 1 MHz and 100 MHz. And you can see that we don't see any very significant harmonics. And that's definitely a good sign. So let me actually increase the frequency just to see when the output frequency changes what the spectrum looks like. So now let me go to the frequency. Let's change it 10 MHz at a time. 10, 20, 30, 40, 50, 60, you can see that we do have some spurious tones here and there, but nothing major. So let's actually keep it as 50 megahertz, and let's zoom in to the signal and take a look at how pure the signal is. And here you are looking at a signal that is centered around 50 megahertz. You can see that with a frequency span of 5 megahertz, and the resolution bandwidth currently is set at, I think, let's take a look, it is at 10 kilohertz. So that's pretty narrow, and you can see the signal here is essentially very clean here, and there is some skirt which is to be expected for any type of DDS signal synthesis, but you can see that the signal is very clean. Now let's do a quick comparison with what the signal output looks like at the same frequency on the UTG4082A. And here is the same 50 megahertz, except this time it's generated by my UTG4082A, as you can see here. And you can definitely see there are a lot of harmonics going on here, and also these are actually only about 30-40 dBs down. Now that is actually still pretty good, but you can see from a spectral purity perspective, there's no comparison between the 962E and the 4082A. Again, I just switched back to the 4082A. You can see how clean the signal is. The signal quality here is really impressive. Another feature I want to demonstrate is the noise output here. So you just switch to noise, and that's the noise output. Now, the noise output can be very useful as well when characterizing the bandwidth and frequency response of an amplifier. It can also be used to test filters too. And when you don't have a tracking generator, having a broad spectrum noise generator is the next best thing to have. And here I have turned on the noise. You can see on the spectral analyzer, and you can see that the frequency response is very flat, between 1 megahertz all the way up to 100 megahertz. That's what we're showing on the spectral analyzer. Of course, the maximum frequency output of the 4082A is only at 80 megahertz. So just to keep that in mind. Another feature I would like to quickly demonstrate is harmonics. If you press harmonics, you will see that we have the ability to choose the order, and that essentially tells you how many harmonics we're generating here. So for example, right now we're looking at order of 2. You can see we have the 10 megahertz and its secondary harmonics. Now if I change this to 3, let's just do that really quickly here. And you will see we have one more harmonics generated on the spectral analyzer here. So if I change it to 4, 5, 6, 7, 8, and you get the idea. That's actually a very good feature to have, especially for testing filters and whatnot. So let's take a closer look here. So right now the order is 8, and let's change it to 7, 6, 5, 4, 3, 2. So that's the number of harmonics we're generating, and I really like this feature. And this feature will definitely come in handy when you're testing amplifiers and filters. So that's very neat. Unfortunately, I won't be able to do a teardown of this unit as it was sent to me on loan from UNI-T, and I do have to send it back. I have been using this UTG4082A for the past couple of weeks while doing the review, and I have to say I really like the capabilities it offers. If you wanted to see me reviewing more of UNI-T's products, please be sure to leave me a note in the comment section below, and I'll try to work with a vendor to make it happen. Anyway, I hope you enjoyed the video. As usual, please remember to give it a big thumbs up, and remember to subscribe to the channel for more videos like this in the future. Your participation makes videos like this possible. Thanks for watching, and I will see you next time.